Hello, and welcome to this PowerFilm, CapEx, and EPs webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenters. With us today we have Sam Jones. Sam is the R&D engineer at PowerFilm Solar. Also with us today is Jeff Colton. Jeff is the EVP at CapEx. And we also have Bruno Damian. Bruno is the Ecosystem Marketing Director at EPs. And with that, I'd like to pass things along to Sam to get this webinar started. So Sam, go right ahead.
Thanks, Katie. Like Katie said, my name's Sam Jones. I'm an R&D engineer at PowerFilm Solar. I've been with the company for almost 7 years now, working on a lot of designs in the IoT space, solving power solutions with energy harvesting. A little bit of background on PowerFilm. We design and manufacture custom solar cells, modules, and panels for energy harvesting. Most of our solutions in the IoT space are using our thin film flexible PV material. We also offer several solutions in other spaces, such as transportation and military with other PV technologies. But there are several aspects of our thin and flexible PV material that make it a really, really great fit for a lot of ultra low power IoT devices, and that's sort of what I'm going to be focusing on today. We are located in Ames, Iowa. We have one facility here in the Midwest. And before we jump into the specifics of energy harvesting and PV technology, it's really great to understand what problem we're trying to solve. And really, you probably caught on from the title of the webinar, but all the problems really kind of revolve around the battery and solving pitfalls of a conventional battery solution. So battery life, limited battery capacity. Developers and designers of IoT devices have to reduce functionality to make their devices last as long as they want. And then this is huge for wearables and some of these next generation tracking devices. Everything needs to be smaller, everything needs to be compact, and oftentimes batteries are just too bulky, and they really are not a great solution for those ultra compact devices. So then how does energy harvesting solve those problems? Well, when you have power, when you're taking advantage of power in the environment, you can use that to extend the battery life, or get rid of the battery altogether, like Jeff will discuss later in the webinar. You can expand the functionality of your device since you have oftentimes a larger power budget. Something that is sort of thought of as an afterthought is really the resilience that energy harvesting can build into a device. Every battery operated device that you have is going to have some sort of estimated battery lifetime with that solution. And that's exactly what that is. It's just an estimate. When you get into the real world, things don't always go as planned. And maybe you lose connection to the cell tower more often than you planned, or you have to push more firmware updates to make your device work. And every one of those unplanned events has a power impact. And you can very quickly start to reduce the estimated that battery lifetime of that solution, and a device that you thought maybe would have lasted 5 years is all of a sudden dying in the field 2 or 3 years in. And energy harvesting is much more resilient to those unplanned events because you can build that into your power budget, and those devices can then recover. And then finally, like I said, some of these more innovative or unconventional energy harvesting technologies, such as our thin and flexible PV material, they can really enable designs that are just not possible with conventional battery solutions. So then getting into the specifics of PV technology and energy harvesting with photovoltaics, two of the really big categories. You can kind of break it into outdoor energy harvesting and indoor energy harvesting. So outdoor light and indoor light. And the metric that's most important is PV output, or how much power are you going to get out of this module. And it's a function of spectrum and intensity. So in an outdoor space, it's relatively easy to characterize these two things with what's called irradiance. And you can go on NREL's website and you could type in any location around the globe, and they have lots of data that says you're going to get this much light this time of year. So for an outdoor use case, there's data available, and it's really easy to kind of build your use case around irradiance data that says exactly how much power and at what spectrum you're going to see that power at. When you move indoors, it's not as straightforward. Light in an indoor space is characterized with what's called lux, and lux is a measure of brightness as perceived by the human eye. And the human eye, brightness is not directly correlated to power density. So just because a light seems very bright doesn't necessarily mean that it has the same power density as another light source. And that's what a PV module really cares about. A PV module doesn't care about how bright a light source looks. They care about how much power, the power density that is contained within that light source. So it's important to understand the spectrum and the intensity of your light source and how the PV module is going to behave under those two conditions. So as an example, we can see here in these two charts comparing a couple different solar technologies under different light spectrums. So on the left you have an LED spectrum comparing amorphous silicon, which is the thin and film flexible PV technology that we use, which has lower conversion efficiency outdoors, comparing that to a crystalline silicon module, which has higher efficiency outdoors, and a triple junction gallium arsenide module that has really, really high efficiency outdoors. You can see that under a low intensity LED spectrum, the amorphous silicon actually outperforms both. And that's just because it is more sensitive to that visible spectrum, and it is designed to operate under those conditions. When you switch the spectrum, on the right side you have an incandescent spectrum. The crystalline and the triple junction gallium arsenide start to outperform the amorphous silicon. So you can see it's very important to understand the spectrum of the light source that you're in your application. I guess the good news is that for most visible spectrums that are commonly used today, so I would say the most common are LED and fluorescent, the spectral distribution is similar enough that you are going to see similar performance for the same lux value under those spectrums. It's when you get into the incandescent and halogen and the solar spectrums, they have different distribution. They have near infrared portions, and that's when you can see some pretty different behaviors from the solar panel. And then the second biggest factor is the absolute light intensity. So in an ideal world, the power generated from a solar panel will scale down linearly in proportion to the light intensity. So going from direct sunlight all the way down to an indoor environment, say on a desktop, you're talking about upwards of 3 orders of magnitude difference in light intensity. So from a solar panel perspective, that's 3 orders of magnitude less power available to harvest on a desktop than in direct sunlight. And with that giant dynamic range, it really starts to show these small material defects. So a traditional solar panel is often designed to operate under direct sunlight, and that's where it's rated. And most will follow that linear reduction of power with intensity down to maybe 50%. And when you start to get lower than 50% direct sun intensity, that's when these small material defects start to become more significant, and they actually start to pull down the performance of the solar panel. And really, when you get in indoor environments, and we see this with smaller cut crystalline cells, where you take a crystalline wafer and you cut it into smaller pieces so that you can have a smaller module for some of these smaller IoT devices. Those cut edges is the process of how it's cut can introduce a lot of defects along those edges. And when you move down into those lower outdoor lighting conditions, shaded on a north-facing wall, and then definitely in an indoor space, like in a retail store, on a desktop, that's when those defects can really pull the panel down to oftentimes zero output. Some other things, those aren't the only things that affect output of a solar panel. The actual configuration of the panel itself and can greatly impact the performance of the device. So when we think about an IoT device, it could be mounted indoors on a wall, it could be wrapped around a pole, it could be outside under a tree. These are really, really irregular lighting conditions. It's not like you could be putting it on your roof, but a lot of times the light profile is highly irregular and it's not super consistent. So one of the benefits of our material is we can design a single cell module in a lot of different shapes and sizes that really mitigate shading effects, which is what comes with the irregular lighting profiles. So in my two examples here, we know from Kirchhoff's current law that if panels that have multiple cells connected in series, if you block one cell, that's going to block current from flowing through the entire panel. But if you only have one cell, if you shade half that cell, the output is only going to drop by 50%. So that is really advantageous for some of these more unorthodox product designs, where the PV and the energy harvesting element is maybe flexible and wrapping, or is going to be subjected to these highly irregular lighting conditions. So wearables, anything mounted in indoor environments, trackers, things of that nature. So kind of putting everything together, how do you choose the right PV cell for your application? You want to understand what the light intensity of your application is going to look like and choose a cell that's rated for that light intensity. So if you're going to be seeing direct sunlight, make sure to get a cell that's rated for direct sunlight. If you're going to be indoors under an LED spectrum, make sure that you have a cell that's rated for indoors under that spectrum. You want to make sure that the way that you design the panel, if it's a custom panel or source that panel, is going to handle the expected lighting conditions. So is it going to be subjected to shading or irregular lighting where a single cell PV is going to be advantageous, or can you go with the multi-cell panel and maybe get a little bit more efficient in the DC-DC conversion? And then finally, will the module that you source survive the expected environment? And I could have gone in much more detailed information about everything that a panel might see in the real world, but things like UV, moisture, impact, abrasion, flexure, temperature, that's just a short list of things that you need to make sure that your panel is protected against, so that you can realize that 5-year, 10-year, 20-year lifetime of your IoT device, and really get realize that ROI of the energy harvesting value proposition. And this is my last slide, just sort of talking about how you can get more information about PowerFilm's products in general and our technology. So we have a lot of standard products. We have development kits. We're launching a new development kit with EPs and CapEx. Super excited about that. I think there's more information on our website for sure. So that'll be great. We have a technical blog that answers a lot of questions that people have, and it's sort of written in hopefully simplistic terms that anybody can gain information from. And then ultimately, if you have an application, we would love to talk to you. So certainly reach out and see what we can do. Thank you, and Jeff, I'll hand it off to you now.
Thank you. Hi, everyone. This is Jeff with CapEx. Quick overview of CapEx Supercapacitors. CapEx was founded in 2000. We're headquartered in Sydney, Australia. We have worldwide operations, and we're traded under the London Stock Exchange under the ticker CPX. We follow a dual market strategy of IP licensing and direct product sales. We make the world's thinnest high power, energy density, lowest leakage current supercaps in the marketplace. And we have, over 20 years, built a really great, best-in-class engineering and Supercap component integration team located in Australia. We license our Supercap technology to several other manufacturers, AVX, Murata, TDK, CDE, and so they use our technology to manufacture caps that they make. We have manufacturing located in Australia, Malaysia, and China. So what is a supercapacitor? Well, first, supercaps are ideal for energy harvesting applications. And as an analogy, a rough analogy, think of a supercap, think of a battery as a swimming pool. And you have a 3-inch hose to fill and empty the swimming pool. So you can only go as fast as you can push water through that 3-inch hose. And think of a supercap as a 55-gallon drum of water. Much less total water, but you have a 30-inch hose to fill and empty that 55-gallon drum. So you can move water in and out of that 55-gallon drum incredibly quickly and incredibly efficiently as compared to the swimming pool. Some of the unique characteristics of a supercap is you can charge them and discharge them 1,000,000 times. They don't care really how many times you charge and discharge them. It's not a failure mode of the supercap. It doesn't wear them out. And typically you design for a 10-year life, but you could design for a 20-year life. You just end up oversizing. You end up increasing the cost of the supercap a little, and the size is a little larger. But you can design for a 20-year life or a 10-year life or whatever your design criteria is. They operate in -40 to 85 degrees C. So a battery is an electrochemical device. In order to generate current, you have to have an electrochemical reaction. And that electrochemical reaction is inhibited by cold temperatures, and the constituents inside the battery are damaged by high temperatures. A supercap is an electrostatic device. Current flows in and out and is stored on a super high surface area electrode. 1 inch of a supercap electrode is about the same surface area as a football field. So it's not inhibited by the cold temperature, doesn't inhibit the flow of the current in and out of the supercap. So they operate at -40 to +85 degrees C. They're incredibly charge efficient, 99% charge efficient. For every amp you put in, you get 0.99 amps back out. And in terms of a C rate compared to a battery C rate might be 20 C. You can operate the battery at 20 times its rated capacity. If you use the same terminology for a supercap, you'd be talking 1,000 C. It's just another way to describe how quickly you can move energy in and out of a supercapacitor. And we make a supercap as thin as 0.4 millimeters, half the thickness of a credit card. There's nothing hazardous inside of a supercap. This is our product line. We have 3 core product lines. On the left is our Prismatic line. This is what we're famous for, and this is the technology that others are licensing. This technology is very thin, low profile, high energy density supercaps. And you'd use these in an application where you have a space constraint. They're a little bit more expensive than the cylindrical cells immediately to the right of them in this picture. And so if you don't have a space constrained application, you probably wouldn't use these because you could get the same functionality in a cylindrical, but it'd be much larger and much larger diameter. So the left prismatics are great and used often in space constrained applications. In the center are our cylindrical cells, and we have zillions of these. These are more of a commodity type cell mounted right on a printed circuit board, and they range from 1 farad to 100 farads. And on the far right are the large cylindrical cells that range from 650 to 5,000 farad. This is a description of our Prismatics. On the left, you see the Supercap. We acquired the Murata Supercapacitor business in 2019, so we supplemented in fact, Murata was licensing our technology, and we entered into an agreement to acquire their Supercap business. We now have 45 different Prismatic Supercaps, single and dual cell. So if you want a Supercap operates at 2.7 volts, say an alkaline battery operates at 1.5 volts, a lithium-ion battery at 3.8, individual cell, and an individual Supercap cell operates at 2.7 volts. And so if you want a 5.5 volt cell, you just put two of them together, and you can see in the third picture, the picture all the way to the right, there's actually two Prismatic Supercaps sandwiched together there at a 5.5 volt cell. And you can put as many together as you want, and you get as high a voltage as you want. And again, we make them as thin as 0.4 millimeters and all the way up to 3.7 millimeters in thickness for a 1 farad device. All kinds of, every imaginable flavor of cylindricals. The applications that these Supercaps are used in primarily are listed in the top, along the top row here in the orange box. So asset tracking, automotive, e-locks, medical devices, a lot of medical devices, point of sale systems, PDAs and scanners. Smart meters is a huge application for Supercaps, because in a smart meter, what you're doing is you're using a battery, very high energy battery to charge a Supercap. The high energy battery doesn't have the ability to discharge at the high enough rate to, say, send a transmission. So the Supercap is charged by the battery, and the Supercap does the heavy lifting of the load, supporting the load. And that's actually one of the main applications of Supercaps, is supporting a battery. It's referred to often as peak load shaving or peak load support, where you don't want to size a battery or pick a battery based on the current required. You really want an energy source, and the Supercap is used to deliver the energy for the application. Wireless sensors, and below here is this is a snapshot right off our website. So if you wanted to research any of these specific applications, you go right onto our homepage, click the application that you want, and all these applications are set up the same way. In the upper right-hand corner on the website, you've got all of these application briefs and application notes, and all kinds of information specific to the application, the wireless sensor or the wearable application, and a case study there. And in order to size a Supercap application, we have created an application worksheet. This is downloadable from our website, but this is the information that we need. This is, a simple drop-down menu application worksheet, and you just download this. You fill in the application, shoot it back to us, and we'll send you a proposal. In the lower left-hand corner, we've got, over 20 years, we've developed a really sophisticated life prediction model. The failure mode of a Supercap is time at temperature and time at voltage. So the Supercaps can operate up to 85 degrees C, but you have to derate them when you operate them at 85 degrees C. So the standard 10-year life on the data sheet would be derated if there was a lot of time at 85 degrees C. But it's time at temperature and time at voltage. And so this table down here has a bunch of slots that you say, all right, it's going to be 10% at 85 degrees C. And so we have a computer model. You plug that in, boom, spits out pretty accurately, very accurately, how long that Supercap will last in that application. And again, this is downloadable from our website. It includes all the information necessary to size a Supercap for an application. This is actually just a picture of where you get it. You go to the home site, you go to the home page, and you scroll down, and you see ask for a proposal for the best Supercap solution, and boom, download the application worksheet, and it's right there. Now, I said that supercaps operate at 2.7 volts, and that's true, but the industry is trying to increase that operating voltage because it has a dramatic effect on the ability of the supercap to store energy. So we have got a 3-volt product in development, and we're sampling that 3-volt product. So it's a 3-volt cell, 3-volt prismatic cell, and that matches up perfectly with a 3-volt coin cell. It saves a huge amount of money. It enables a coin cell or energy harvester to power applications directly from a direct coupling, and so you don't need LDO or buck boost device. And by operating at 3 volts, we can basically extend the battery life. And in this case, a coin cell, you can extend the battery life 22% over 3 years, 30% over 5 years. It reduces the system size by eliminating the LDO or the buck boost or a second capacitor. So if you're operating a supercap at 2.7, but you needed 3, now you'd have to use 2 of them. Now you can just use 1. So we have high expectations for this new 3-volt device, and again, we have it. We're capable of sampling it now. It's not in production, but we're capable of sampling it, and very interesting to develop beta customers with this 3-volt cell. In the lower left-hand corner, you'll see the formula for energy, E equal 1/2 CV squared. So V squared, voltage squared. So if you increase the voltage from 2.7 to 3 volt, you square that. You square the increase. And you can see that has a dramatic impact on energy. C is capacitance, so 1/2 capacitance times voltage squared. And again, this is my summary slide. So we've got, again, the primary applications that these caps are used in are listed here. This is another snapshot from our website, and all of these applications are listed with very detailed information. When you click on the individual application, you'll see very detailed information and application notes, application briefs, more than you probably want, available on our website, www.capex.com. So thank you very much. Bruno from EPs is next.
Yes, good evening, good morning, good afternoon, everyone. My name is Bruno Damien. As you can guess from my accent, I am a French guy working in Europe, and it's amazing to see those 3 companies, one from Australia, one from America, and one from Europe, joining efforts to make this presentation about designing perpetual IoT edge device using solar energy. So what I would like to show you today is a quick introduction to our company, who is doing best performing ambient energy harvesting power management ICs, as well as processing and sensing, and combining this technology with partners like CAPEX and PowerFilm to create solutions for energy storage and applications. And I will go through a folder that is more applicative in this presentation. So quick notes about EPs. Our mission is to focus our activity in making sure that people can harvest more energy from their energy harvesting system, store it, and consume less from the application side and from the processing side. And that's a quite challenging perspective that we have started at EPs to work on in 2014. So it's not really a first guess and a first start. And I personally joined EPs a few months ago after having spent 8 years in energy harvesting technology for other companies. So the power management IC, as you can see on this drawing here, is really something that is sitting at the heart of an application between the harvester on the left the storage element on the right, and your application. So you can be from the harvester side, the storage side, or the application side. In the middle, you need a PMIC that is acting like a sort of switch. And it's not an easy task because we do it to manage with the minimum of energy losses and tracking the maximum power point of the energy source, and apply this to efficiently convert energy to the storage element and make it available for the application. So we have a pretty big family of 15 products that are shown here. Those products are made to support either energy harvesting from light, from thermal, from AC sources, or from pulsed source. Here today we will discuss essentially of a context of a boost application. So we will focus specifically on the first top one, which is AEM 10941, which is a boost product. Why? Because as said Jeff before, is CAPEX Supercap that we have selected have a 4.5 volt storage element level, while the PV element from PowerFilm is producing from a nominal voltage at 2.5 volts. So we are really from 2.5 to 4.5, we are really in a boost configuration. So we prefer to use this one here. We might have selected the other one below, but let's go for this one first. So our EVK, because we are speaking of a combination of EVK of 3 members of this alliance, this EVK is designed to get free of charge electric energy from the light. That's an exciting program, and let's have a look how we do it. So we said that we generate energy from the PowerFilm PV cells, and the one we have selected today is the indoor one. Sam has explained to us the difference between indoor and outdoor performance. In the EVK you will get from the market that we have designed for you, you get both samples. Today we will focus on indoor. We could have done something else, but from indoor energy at 1000 lux, we can get 450 microjoule per second. Remember this number because we will reuse it later on. And that's pretty cool number. Now we have also a side of our PMIC, we have a storage element, which is obviously a CAPEX Supercap. And as you can see on the left, the voltage of this storage element provided in the EVK is above the source voltage of the PV. So really, we are here in a boost configuration. And from the energy we can produce in the PV cell and what can be stored in the CAPEX Supercap, which is about 2 joules, we can estimate that we can charge quite rapidly, fully from 0 volt, this Supercap element in about 1 hour and 12 minutes at 1000 lux. This is quite cool because out of the box, you just have 1 hour to wait before to have fully charged operations. Note that you can start working before being fully charged. In the middle of those 2 elements, you have the PMIC, which has several value propositions for us today. We spoke about the boost capability, but it's not only that. In yellow, you see additional value proposition like super low voltage cold start energy and voltage. We have also available device status digital outputs that inform you about whether your system is ready to work or has to wait for having more energy, plus other many things which are very interesting. So the low leakage current, very important because when you produce 50 microamps per second, you don't want to draw them into the surrounding electronics. So here we have extremely low leakage current that preserve your energy. We have smart presets, and that's also a cool feature for the EVK because you can very easily configure the kit so that it works conveniently with the PowerFilm PV and the CAPEX supercapacitor. That's really cool. No need for MCU to make the configuration of the system. And additionally, we have smart LDOs. Smart means that you can use them or not. And if you decide to use them, the system, the PMIC will wait that certain level of energy is stored in the storage element before to activate the LDO, so that you can fast charge your storage element. Now, what is the EVK? So we have combined different elements. You see the PowerFilm indoor and outdoor PV here. You see also the CAPEX Supercap, and you see the EVK that is having at the center our PMIC here, a little boost self, and all connectors required to connect either your application here, your storage element, your configuration pins, and so on and so forth. That's really easy to use. You have also status pin here that you can use to control if your system is working waiting for being energized enough, and so on and so forth. You have also specific features like this one here, the balancing control. As said by Jeff before, Supercap can be made of a sandwich, and sometimes you have two Supercap in series and you need to monitor the balancing pin, the central pin, and that's possible with the EVK. So let's see how that works together. So we easily configure our EVK. As we said, we just have 3 jumpers to set to say what is the voltage range you want to work around. So we say Supercap can work up to 4.5 volts. So we protect it by selecting this configuration. We want to use an application that is supplied with 3.3 volts. So this setup is perfect for us. Note that a Supercap can do much more than discharging down to 3.6 volts here. So you have also available a custom configuration setup that allows you to do more. We did not want to activate it. We want to keep it simple for you. You guys at development, now you can take hands on it, put hands on it, and work. So our application is shown here. We have the EVK with the PMIC in the middle. Backside, you have the CAPEX Supercap device. Here we have connected an indoor PV from PowerFilm, and here we have selected an application board that is a data logger, temperature data logger, that can be programmed and read out by NFC, but this kit needs a CR1225 coin cell to work and to data log the temperature. And obviously, what we want to do here is to get rid of this little coin cell. So we have defined our environment, and now we are capable to make it work. So the first thing we want to do is to estimate how much this application will draw of energy with our configuration. So what we have done is we have configured a duty cycle of a measurement every 15 seconds, and with some off-the-shelf energy controller, we can easily see that we can withdraw an energy of 243 microjoule every 15 seconds with this application. Good enough. We know that we can produce every second 69 microjoule at 200 lux, which is 1035 microjoule every 15 seconds. So if you compare, you see that our application is drawing much less energy than one we can collect at 200 lux, and needless to say that at 1000 lux we are really comfortable. So what we will do, we will collect this energy during daytime and use it for the application, and we will store the surplus of energy into our Supercap for nighttime. And this will be very funny to work with, and this will work like this. So on the left, we have the PowerFilm PV cell giving this energy to the PMIC. The PMIC will charge the CAPEX Supercap element, And once there is enough energy, we'll decide to switch this energy to the load. And usually, once this level of readiness of energy is passed, the application works forever. So we just give a kick at the beginning, at the cold start, to enable the Supercap to charge from 0 to the V charge ready. And once it's done, we go and we supply the energy thanks to the autonomous state machine of the PMIC. The PMIC, you can see it here, is really the heart and the sort of smart system that control everything around it and can supply the energy to the load, which is here our NFC tag. And what does it do? Here we have an application that is not provided in the EVK, but that is enabling you to read out the content of the measurement that has been done. You can see here that we are running day, night, day, night, day, night, and collect temperature information. I have it inside of me. It's running for 8 days, providing tens of thousands of measurement points. And this, so that you can use this application for data logging, either for cold chain application, for medical application, for vaccine monitoring, and so on and so forth, all powered with free of charge energy from the light. That's really cool. So, in summary, the value proposition of the EVK that we propose together, if I just look at the PMIC and PowerFilm side, we support both indoor and outdoor PV cell with high efficiency maximum power point tracking. That's the way we collect the maximum of energy from PowerFilm devices and store them into the storage element. We have a wide input range, which is important for the harvesting source, of course, because during the day and the light, we have seen that the range can be wide. And we have also ultra low power startup, which means that just at the blue hour or golden hour, we can start collecting energy and store it and make good use of it, either with the application or the storage element. If you look at the side of CapX and Supercap, the value proposition is that we have seen that CapX Supercap can draw a lot of current. So we have to be capable to to manage this high level of current, and we can do it with our PMICs. We also provide automatic support for over voltage conditions and under voltage conditions. So in a case of Supercap, the most important one is over voltage, as you can quasi completely discharge your element without creating troubles to it. And also, nice but not least, we support single and dual cell supercapacitor put together in series. So that can be very, very interesting for the Supercap environment. And finally, if we consider the system level value proposition, we offer optional LDOs. We have buck and boost behavior so that you can harvest energy and convert it with a very high level of efficiency. We have ultra low quiescent current, which means that you can use completely the energy you produce for your application and not to lose it into the PMIC or other surrounding elements. And we have an MCU-free operation, which means that you really can, you will not affect your application MCU with the PMIC. The PMIC by itself is standalone. It works, and you don't have to bother and develop code for configuring the PMIC, thinking of how to start with, and no, that's really what we take care of. And you have also some status mode feedback, which are available for you for your development or for your application later on. That being said, we have demonstrated that with a tiny PV cell from PowerFilm and a CapX Supercap, combining with our high-performance PMIC and a smart sensor node, you can make it work battery-free with energy which is free of charge and maintenance free forever. So this is based upon our new EVKs. There is a little typo here, sorry for that. The EVK is compound of our EP's PMIC and a PowerFilm, two PowerFilm PV cells and different CAPEX storage elements. And as I try to show, it's really easy to configure. You can replicate this configuration in 30 minutes or so. With that, it's my last slide. It's time to go for Q&A.
All right, Bruno, thank you so much for that last section of the presentation. So Sam, Jeff, and Bruno, thank you all for such a great presentation. So for our attendees, we are going to move into asking some of the questions that you've submitted now. We do have a lot of questions listed here, so we have about 12 minutes to take some questions. So I will say that we do not have time for all your questions live today, but if we don't get to your question, please do not worry. We will reach out to you following today's webinar. So for the attendees, if you have a question, you can use the Q&A window and click submit, and your question will get logged into our queue here. So gentlemen, we're going to take as many of these as we can fit into our time here. So the first one today, what is the expected life of a supercapacitor?
Hi everyone, this is Jeff with CapEx. The Supercap life is defined either in number of cycles or number of years. So in number of cycles on the data sheet, it starts, say, a definition is 1 million cycles, 1 million charge-discharge cycles, or a number of years would be 10 years. But it's really dependent on the application. So if it's a high temperature application, it could be less than 10 years. If it's a very cool application and low voltage application, it could be 20 years, or if you oversize the Supercap, it could be 20 years. So you design the Supercap to the specification of life requirement. It can be as long as 20 years.
Okay, Jeff, thank you so much for that answer. All right, gentlemen, our next question, how is PV material made to be flexible?
Thanks, this is Sam. I could do a whole presentation going into all the details of all the process steps, but I'll give you the short answer. We start with a roll of polyimide Kapton plastic, 10,000 inches long, and it goes through about 12 different roll-to-roll processes where we deposit the different layers using vacuum chambers, printing steps, screen printing steps, laser steps to define the different features and configurations of the PV material, and then finally gets die cut out. So it's all monolithically assembled and integrated into a solid, flexible piece. It's about 0.2 millimeters in thickness, and the flexibility, I mean, we could wrap it around a pencil in certain configurations. So it's also very dependent on application. But it can be extremely flexible and durable.
All right, Sam, thank you so much for that answer. Another attendee is asking, what I want to know is the effect of the solar cell if covered with a strong see-through cap, like, for example, glass, like on a road stud.
I'll take this one too. Anything you place above the solar panel will reduce the amount of light that gets to the panel and thus reduce the output. Some materials are better than others. Polycarbonate tends to have very good transmission. So it really depends on how clear, how transparent, what the surface interactions are. So if the PV is mounted with like an adhesive to the glass, if there's a air gap between. So there's a lot of different ways, but I would say the reduction of power output could be anywhere from 5% to 50% if the cap is, or if the glass is tinted. But that is often a solution that our customers use to implement some of the higher level protections, especially in an outdoor environment, that may be required to get that long lifetime for an energy harvesting solution.
All right, Sam, thank you so much. And then just a reminder to the attendees, we do have a lot of questions to get through today, so we won't have time for all of them. We will reach out to you following today's webinar if you do not hear your question being asked. So next one here, gentlemen. Can the flexible solar cell be used to charge the Supercap instead of reusing the rechargeable batteries?
Jeff, you want to go ahead and take this one?
Sorry, yes. Could you repeat it, Katie?
Yeah, sure, I can repeat it. So this person is asking, can the flexible solar cell be used to charge the Supercap instead of using the rechargeable batteries?
Yes, absolutely, and that's the beauty of the Supercap and this whole application and the EV kit. The whole system is designed to eliminate the battery and have be almost a perpetual energy machine. So yes, the Supercap can be charged from the solar cell, and then the Supercap does powers the load and takes the energy from available energy that's available for free, light energy. So yes.
All right, Jeff, thank you so much for that answer. All right, our next one here. I have used supercapacitors in most designs over the last 5 years. One of the biggest challenges is the initial charging of the capacitor, where the inrush currents brown out chips, trigger safety latch off on the LDOs, and etc. Does the AEM 10941 handle this large inrush gracefully? Are there any recommendations that are cost-effective to handling supercapacitor inrush currents?
So let me try to answer this question. So first, in fact, we don't use the LDOs of the AEM 10941 to charge the Supercap. The LDOs that are on board can be used to draw energy from the Supercap and direct it to an application that is connected to it. And there are limitations of current from these LDOs, which are specified, for example, on the datasheet of the device. You can see 20 milliamps to 80 milliamps from the Supercap to the application. That's one point. Second point is charging the Supercap itself is something that we do natively with the AEM 10941. It's one of the options of storage element. There are 3 versions of Supercap charging. What I would like to check with you is what size of Supercap are you speaking about? Is this commercial device like we speak here with the CAPEX product of the EVK, or are they big ones like the ones that are used in aircraft to trigger security applications? That's something I would like to check and revert to you with an answer. But definitely, as of today, an AEM can manage charging from 0 to overcharge level a Supercap as the one we have discussed today.
All right, Bruno.
This is Jeff.
Go ahead.
We have a great application note on our website about managing inrush current and current limiting to charge the Supercap. So there's a very nice application note on our website that gets into the really specific details about how to handle that issue.
All right, thank you, Bruno and Jeff. So as I mentioned, we have a ton of questions listed here. We appreciate all of you participating, and we will get through all your questions. It just won't be live today, so we do appreciate the time you guys have spent. So gentlemen, we have about 5 minutes left, so this is going to be the last question that we take for today. This one is asking, in the proposed solution as explained today, do we need any external microcontroller, or the AEM, does that take care of all the MCU functions?
So the answer to that is no, the AEM does not take care of the MCU functions because An AEM has no MCU on board. It's a sort of little system that runs alone without the intervention of an MCU. There is the necessary circuitry in it to enable taking the energy from the PV cell, storing it to the CAPEX without MCU. However, it's obvious that making an application like an NFC data logger with connectivity and also Bluetooth connectivity is not something a state machine can handle. So there is a need to have an MCU somewhere, and this is, if you remember one slide of here, this is a function that is taken by the application board. What we did with this example is take an off-the-shelf application, remove the battery, replace it with an energy harvesting solution, which is provided by our EVKs. That's just what we did.
Bruno, thank you so much for that last answer. So as I mentioned, everyone, we are going to wrap the webinar up right now. We are at the top of the hour. I would like to say a huge thank you to Sam, Jeff, and Bruno for sharing all of your expertise and for answering some of our attendees' questions. So gentlemen, thank you all.